series on PCB design topics, and thank you for tuning in to discuss what a PCB layout designer should know about signal integrity. Here with me today are two subject matter experts in the field, Myrna Winneck, technical marketing engineer for Expedition, and Weston Beal, Hyperlinks product specialist, both of whom are with Siemens. Thank you both for joining me today.
Pleasure to be here. Thanks.
Good to see you, Steph.
Awesome. This is a great topic. So, signal integrity is one of my favorite topics, especially when it comes to PCB design. So let's just dive right into it. When we think about signal integrity, let me ask this first question. If you're not an expert in SI, what do I need to know about SI in PCB design? Weston, I'll start with you.
So there's a Dr. Eric Bogatin. He proclaims he's a signal integrity evangelist. And he says there are two types of layout engineers, those who have signal integrity problems and those who haven't found them yet. So basically, every design will eventually have some signal integrity problems. We used to say when we were moving in, kind of starting signal integrity, what is high speed? At what point do you consider it high speed? And so, there was a lot of discussion about a certain data rate or frequency or rise times and trying to pin down a number. And finally, somebody said, actually, anything that's significantly faster than what you've designed it before is high speed. And there will be new things that you need to worry about.
Vernon, you want to add anything to that?
No, I mean, I agree with that. And, coming from somebody like myself, a PCB designer who's not a double E, I'm not an electrical engineer. And most PCB designers in the world today are not electrical engineers, but we have to learn some level, base level of signal integrity when we're doing our designs, because like Weston said, we're going to, we just haven't found the problem yet. So we work directly hand in hand. Most layout designers learn to work hand in hand with a electrical engineer, and we learn the basis of simple signal integrity. And we leave the heavy lifting to the double E's and everything. But we always have to have some sort of base information and base technology that we can utilize in the tools to do this easy, performance signal integrity as we're starting our designs. And it all starts right up front, with things like stack ups and preliminary simulation coming from the engineer. So, and I'm sure we're going to talk a little bit more about that. So we'll get into that a little later. So,
oh yeah, we'll definitely dive into the nitty gritty there, especially when you talk about where are the signals, where should you route them within the stack up and the first planes, and yeah. But when we think about signal integrity, right away simulation and analysis come into play. So let me ask this next question: is why is signal integrity, when it comes to analysis simulation, a vital part of the design? Vernon, I'll start with you this time.
Well, as Weston said, the problems we're going to run into in high-speed design, most of us as designers haven't found them yet. We're going to, as we're routing a design, each design we do from day to day, we use the term high speed now almost as, it's just a normal, but we don't realize every day the term high speed changes. The boards get faster and faster, the frequencies get faster and faster. And as this stuff occurs for us as PCB designers, the boards just get harder to route. We have to deal with densities. We have to deal with minimizing layer content for like commercial product. The more layers, the more costs. We're minimizing things, and when you think, oh well, I'm going to minimize the number of layers, the board gets easier. No, the board gets harder. There's a lot more involved with signal integrity when you start removing things like plane layers and stuff that used to, help your signals before. They're not there to help anymore. So we have to do a lot more different things when we do a design these days.
So going along with that, one thing that makes it more difficult is, I like to say, well, it's true, every trace is a transmission line. So every transmission line has a delay, and every transmission line has impedance. And whenever there's an impedance change as the signal propagates through the channel, there's reflection. So it used to be that things that were like a half inch or an inch long really didn't matter. The signal edge rates were slow enough that that inch just kind of got just washed out. Now, where we have those edge rates so fast, now that inch is really important. And that's why it makes it so much more complicated. As those edge rates get fast, smaller and smaller entities that we used to be able to overlook now become significant. And we have to watch out for every one of those.
Yeah, I agree. I think it's a misconception to think, well, I'm running high speed. It's more of what are your edge rates? What are your transition, from high to low, low to high? What is your edge rates? That is the critical thing to focus on. If you attend any of the industry conferences that are out there, you'll hear, Rick Hartley, Eric Boton, or Dan Beaker, talk about, you know, edge rates and that transition and what you need to be mindful of regarding, your performance of your board. And bottom line is, when it comes to printed circuit design, it's about controlling the energy in the board. How are you moving the energy? And that's the key. So when I think about, signal integrity or signal analysis within the design process overall, when would be, or let me ask this better a way is, why is it not, why shouldn't we skip that step of analysis when we think about, the overall process? Because there's been many a times where I've been on projects where, the project manager will come and say, we don't have time for analysis. Let's just skip it. So why is it vital not to skip the step for the sake of reducing project time or money? Weston, I'll start with you.
So let me tell you a funny story from years ago. I worked at a computer company, and one of the layout board engineers, he came to me and said, "Hey, will you help me analyze this bus, whatever it was?" And I said, "Well, so it looks like from the name on the file, this is like revision 5. So you must have done some analysis on this before. Where are the models used?" He said, "No, we didn't have any. We have not done any analysis yet." So wait, you're on layout revision 5, and this is the first time you're simulating anything. And he said, "My manager didn't put any analysis in the schedule, but he did put in 5 or 7 respins of the layout." And it's just like, so how long does it take to do a respin, build the board, get it in the lab, and test that? I mean, that's weeks and weeks. Whereas once I got the models, it took me a day, 2 days to simulate and find where the problem was. So simulation finds problems much faster than doing a board spin. And if you wait until you think the board is all laid out, and then the signal integrity engineer or whoever's doing the simulation comes and says, "Oh, you have a problem right here. You need to change this layout." Well, if everything's already packed in there, like Vern said, we've reduced the layers and everything's packed in as tight as we can get it. Now it's going to be another week to revise that layout. If we know up front, if we start in, okay, here's my board, these are the nets, these are going to be the fastest nets, I'm going to need to worry about those, and I can simulate that pre-layout in a schematic form. I can find out, okay, what's impedance I need to watch out for, what are the critical lengths between components, does it need termination, and figure all that out before, then I can put those constraints into the layout when it starts and get it right the first time.
Yeah.
Vern, you want to add?
Well, no, and I've got a similar story. Before I worked with Siemens, I worked with a company that, wouldn't even buy simulation tools. They said, we don't need to simulate boards. We'll just rebuild it, and
My
they didn't.
goodness.
And until we were doing, 2,000 to 3,000 designs a year and rebuilding each one of those and having to pay for new boards to be fabricated each time, they didn't realize how much money they could save. And and I think from a standpoint of a design company, and the layout engineers were, simulation is this big word, right? It's this big 10,000 foot word that we think of simulation is everybody sitting around with probes and an oscilloscope and trying to, but they don't realize that simulation starts, in layout with a basis of a good PCB stack up foundation, knowing your enclosure, knowing your number of layers you're going to work with, knowing your impedance stack up, and building that with your fabricator. These are simple forms of simulation that all lead to that probes and oscilloscope simulation somewhere down the line on a workbench. But but simulation, like Weston said here, from within a schematic can be done. We have differential pairs we can test. We can test for, what's going to be the crosstalk issues with these things. What's going to be where do we need to place these high-speed signals within a board to keep them protected from other high-speed signals. This is simple simulation that can be done instead of, these companies that thought, if I buy a simulation tool, I'm going to have to buy a bunch of engineers who know how to run it and a bunch of, and so, yeah, it's, simulation is, like I said, I'm going to say it's a 10,000 foot word, and you can run it from the 10,000 foot level. We'll get down to the 1,000 foot level, but you got to start somewhere. And if you don't start
Yeah.
at all, it just costs money. That's all it is.
You're absolutely right. And I would tell you, when you think about simulation and the overall design process, when and how often do I need to perform SI analysis or simulation during the process itself? I mean, Weston, what would you say?
It depends on the experience of the team. And it also depends on the net. For example, when, years ago, PCI 33 was like, oh, now what are we going to do? So we simulated a whole bunch of stuff. But we've done enough of those designs that we know what the constraints are. If somebody's still doing PCI, we could just put it in there and it would be right. It would be fine. When we started into gigabit Ethernet, I was like, okay, now we got to be really careful with these differential pairs, and we got to do all the length matching, and we got to check this and check that. Well, now we've done a few. Okay, we know, we just put it in there and we put these components next to each other. It's fine. If it's high speed, if it's faster than anything you've done before, simulate as soon as you know you're going to implement that bus. Figure out where are the pain points, what's going to hurt us, and get the constraints into the layout at the very beginning. When things are looking tough and the layout guy says, hey, I don't know how this is all going to fit together, we might need to revise some layouts, do some simulations and figure out what we can revise. And then when it's all done, double check it, do that verification at the end to make sure everything was done correctly before you go build it.
Yeah, and
Right.
I would say, similar. We, as layout engineers, we're working as fast as we can to get the board out the door. That's what we're doing. But we know, and like we said, we have these best practice circuits, PCI, DDR, we've done them so many times, we can pretty much route them in our sleep and know that they're going to pass analysis. But the minute we get something new, a new RF circuit, a new analog circuit, things like placement come into play, where we may need to tweak the placement. Just the rotation of a singular part can cause a problem. So at that point, as Weston said, that's when we have to say, we have to stop, sit down, analyze just that circuit, work with an engineer and tweak that circuit to perfect, so that the next time we have a best practice circuit we can use as a reuse template or something, and then carry it through 1,000 designs and know that we've already analyzed it and it'll work the next 1,000 times that we put it in the design. So,
Yeah.
So one more point on experience. If you're doing a DDR4 and you've never done it before, you might connect all the dots and say, well, yeah, it looks good, but you don't even recognize where the problems came into that. After you've done 10 or 20 of those buses and you've analyzed them, found the problems and corrected them, a layout designer now can look at the board and say, that looks good. Based on my experience, I can see visually that that is a good design. So that one probably doesn't need to be simulated up front 5 times. Just do the verification at the end. Yeah, it's good. We did it right.
Yeah, as
I
long
agree.
as
I
you,
think when it
as long
comes
as you
to
meet those
yeah,
constraints, right? So,
yeah,
look,
I think when it when you talk about the evolution of the designer, um, either his or her experience as they evolve and master their craft, if they're implementing best practices in how they attack their design, they can learn from previous analysis and learn what the effects of routing traces in a certain manner that will help reduce the amount of simulations that's required because they already know from experience, I did this last time and this is what the effect was. So now if I do it in the same way, I can get a positive result I want. And I think that's key is the evolution. When you think about what you gain from doing the analysis, and I would never recommend skipping analysis. At a minimum, I think it's critical that you do at least 2 analysis, one for critical nets, and then if you're not going to do anything else or another analysis, at least do one at the end uh, to see where you finalize. Because the worst thing to do is to pull the trigger and you have that board already cemented in stone, and now you can't change the physics of the board
yeah, and that's
or anything within it. That's
yeah,
it's
and that's
catastrophic at that point.
and I think another thing, we talk about when and where to do analysis. We have these best practice circuits we talked about. Let's go back to
Mhm.
DDR, the example of DDR. Done the DDR for over and over and over again, and I know it's right. And then all of a sudden, because of some reason, the the environment the board is going to go into or something, engineer comes in and says, we're going to change the material. We're going to build the board with a different material. The circuit route's the same. The material causes a huge problem that we now have to analyze for and see, did it affect the circuit by changing
Yeah,
just the material in the board? And those are those
yeah,
stop points. If anything changes, reanalyze. So,
yep, yep. Weston, go ahead. And
So
you got to
that's
say
where
something.
the experience of the whole team comes in to recognize that at least something that we're changing is going to affect signal integrity. They don't have to know all the details, but if they know which inputs are going to change the output, say, hey, we need to stop and reevaluate this.
We're talking about material here now. Let's move over to the stack up. Why is it important to establish a good PCB stack up foundation when you talk about you know a board structure and especially regard uh, performing a signal now simulation and analysis. Weston, you want to go ahead and start with that one?
Okay. Yeah, I was going to let Vern go.
oh, go ahead,
Um,
Weston.
so
No,
Uh,
no.
So
Yeah.
like I said, every trace is a transmission line, and the delay and the impedance of that transmission line is directly affected by the material and the geometry. So the distance from the trace to whatever reference, whether it's a plane or a guard trace on the side, all of those things around it affect the impedance. The impedance needs to be constant through the entire net. So we need to examine what are the different impedance requirements that we have. Some nets or some buses require different impedances. We need to see that we can get a stack up that provides the right geometry so that we can get the target impedance for all the different buses that we're going to route through that board. So we might say, okay, we can put this bus on the top layer because we can get this impedance with this specific dielectric thickness. And by changing the trace width, we can change the impedance somewhat. And then on an inner layer 2, we'll put the other impedance because we have the right stack up in the material for that.
Yep. And as a layout designer, I am always looking, layout stack ups become important because I'm looking for the physical issues within the board. I'm trying to stuff, 10 pounds into a 5-pound bag. And that means I have to adjust trace width, spacing, layers, that the number of layers I can route on. And all of those things affect those high speed signals that we talked about. And if we don't get some sort of idea up front, by getting a baseline stack up, a baseline set of materials. I just mentioned, engineer will come in and say, hey, I want to route a board on these materials because it gives me the best signal integrity I can get on this board. And then when we go to fabrication for commercial application, we've decided instead of building 10 boards, we're going to build 10 million boards like an iPhone. They change the stack up and they change the material. And it's like, I have to go through this all over again. I have to, I have to make everything fit into that board, but it's not only got to fit physically, it's got to fit signal integrity wise too. So,
Mhm. When we think about the board stack ups, what's a good basic PCB structure for, that like would really cater to good, simulation and analysis, or whether it's signal integrity or power integrity? What would be a good structure in general? I know one of many questions I get asked at trade shows is, hey, what's a good stack up? And to me, it's kind of like a very open-ended question, because a good stack up is the stack up that allows you to be successful in meeting your requirement. And because it could be a varied, whether it's, a 6-layer, 8-layer, 12-layer board, it just depends, or maybe even, 30, 40 layers. It all depends on the structure. And when I think of the structure, I think of trace routed adjacent to its reference plane, or a tightly coupled power and ground plane. Weston, what would you say, especially, coming from an SI expert, what would you say would be a good structure?
I agree that it's really difficult to come up with one general answer because different products have different requirements. Are you looking for performance without consideration of cost? Are you looking for low cost and it's okay if it crashes once in a while? Are you looking at low numbers where you don't care about cost, or are you looking at millions where cost, it's different for all those cases. But with that said, in general, we want to have a solid plane next to each routing layer. And remember that your power nets, usually routed as area fills, also count as reference for the signal, because it's about the electromagnetic field propagation, not just the current. And that's what determines the impedance. For power integrity, it's very helpful to have every power plane as close as possible to a return or reference, or sometimes we call it ground plane. That's very helpful. Not required, but it's a good benefit. So take all those things into consideration, along with your cost and performance requirements, and come up with something that works.
yeah. And I'd have to say, I've been doing this, 40 plus years routing boards. I've never seen a perfect stack up. It doesn't happen. I coming up, through the years, Bogaton and Hartley, they had documents that said your best stack up, has planes on the outer layers. Well, I got thousands of parts on the outer layers. How do I put planes on the outer layers? And then there were people that said, you have to have a plane between every signal layer. And then they said, oh, well, if it's differential pairs, or, you could run them, broadside, with asymmetric, impedance, layers, which is plane, two signals, and a plane, stack up. So there's no perfect answer to that stack up question. I think, one of the things we talked about, preliminarily, before we did this podcast is, and Weston just mentioned it, there's a power problem, right? And your power distribution in the board is going to have a huge effect on where you route these signals and how you do your analysis in the board. Because, back in the day, we had one power, VCC, and we had one ground plane, right? What VCC and ground, one of the most recent boards I looked at, it had 34 powers on the board.
Mhm.
So, this is the world we live in today. Things change so rapidly.
And
Yeah.
That power distribution becomes very important, and it affects everything. So,
and back then, we didn't even worry about making it a plate.
yeah,
Your
Exactly.
power could just be white traces going out there. Oh, we'll put a big decoupling capacitor right next to the component. It'll be good. Yeah, not
Yeah.
anymore.
So when it comes to stack ups, one of my uh, um, like bullet points that I always mention when I'm speaking at the conference is communication with your supplier, collaboration with your supplier is paramount. You can't communicate enough. When's the last time you picked up the phone and call your supplier? So, why should, if you're a designer, why would you recommend utilizing a manufacturer to get your stack up in place?
I, in our previous talks, Stefan, in our, previous two podcasts, we talked about coming up in the industry. I have worked with companies that never contact their manufacturer. They put everything down on a drawing, and they figure when they send this drawing with the fabrication data to the manufacturer, they're going to get exactly what they put on the drawing. That never happens. The manufacturer has to change things. The manufacturer has process changes that they have to make. And I stress to every customer I deal with that does design, one of the first calls you should make after you receive the schematic from the engineer is to your manufacturer. I've got a board coming. It may be in a week. It may be in 6 weeks. It may be in 6 months. But I have got a board coming, and I want it to get through your shop as cleanly as possible. And I don't want you waking me up at 3 a.m. saying, what does this mean on your drawing? So the very first people I call are the manufacturer. And that starts this whole process rolling, because as the engineer makes these changes for signal integrity and everything, I can immediately notify my manufacturer there has been a board change, and that board change may affect them as far as with something as simple as I need to order this much more material because I don't have that material in house. So, it's very important to be in touch with your manufacturer at all times.
True.
So,
And it used to be enough that we could specify, hey, we need this kind of layout to get these impedances and send it to the manufacturer, and it would be close enough. Close enough now is getting smaller and smaller. And so we should do the initial stack up analysis and say, this is what we need, send it to the fabricator. They know their process. They know where they're going to have to adjust some things here and there. And then they can feed back and say, okay, you can get this impedance. Oh, along with the stack up, we need to specify these nets need to be this impedance. And they will adjust and send back the data and say, to get this impedance, we're going to adjust our process like this because of this material and whatever. And we know the over etching and however that happens. So you need to adjust these widths on these layers by just this little bit. Now we can take that data and feed it back into our analysis or our simulations and get a more accurate answer. Whenever I do simulations for customers, I say, okay, of course I need the layout, and the other data I need is that stack up from the manufacturer, from the board fabricator, on how they will create the stack up with the exact materials that they're going to use and the exact dimensions. And that's what I put into the simulation. And it really needs to be that way for the final verification.
and we have hundreds of other processes as designers that we're going to feed to the manufacturer too. We don't just tell them our impedances and the number of layers and things like that. We're going to tell them, we're going to use blind and varied vias. We're going to use laser vias. We're going to do different things in the stack up for these types of signals. And they're going to feed back all of that information on how they handle those processes in manufacturing and how they will affect us in our signal analysis, based on the features that we're going to use in our routing of our boards. So,
Yeah, we talked about material and the stack ups. So let's mention a little bit, or let's dive a little bit into the material itself. So, what is the significance of material choices, and how does the material affect signal performance? This is something we definitely need to, talk about.
So the first thing to worry about is the dielectric constant. I mean, that's what we use primarily for decades. That is the primary effect on the impedance and the delay. Then, as we get into higher speed, we run into dielectric loss. The material property is the loss tangent, sometimes called epsilon sub. Well, they have different names for it. There's the DF. They call it the dispersion factor. And that is a high frequency loss that occurs in the dielectric. Usually it kicks in hundreds of megahertz or maybe 1 gigahertz. And so most of our high speed SerDes, our fast SerDes channels are running at that rate. And so we have to worry about loss. Now, fairly recently, we're worrying about the fiberglass weave in those in the dielectric layers. And when we're routing differential traces, the actual dielectric right under a trace, right where it goes through the bundle of fibers, is different than if a trace goes over a gap in the fibers. So there's been a lot of development on doing different fiber weaves, doing different techniques to avoid that problem. And so those are the three things. First, the dielectric constant, the loss tangent or dispersion factor for high-speed loss, and then the fiber weave and how are you going to deal with dielectric differences and then the delay differences caused by by the fiber weave. Yeah, I think that's
well. Yep.
Oh.
And for me, as a simple layout guy, my first thing is the dielectric constant, the ER value, right? That's how that's where I'm going to start creating my impedance calculations in my layer stack up building inside of the tool that I'm routing in. The ER value becomes the most important thing for me because that's going to get me my baseline impedance that I need to do for routing. Of course, we're always, engineers are always screaming at us about, inductance and capacitance and, coupling and things like that. And, we work with them directly to get the, you mentioned fiber weave. It's one of the things that's recently come up in the past few years where, okay, we've got to we can't route parallel with the fiber weave of the material. So there's two methods to go against that. And that's either the manufacturer can rotate the material to a certain degree, or we can rotate our traces to a certain degree so that we're not doing parallel routing over the fiber. So we have to know that stuff. And that's one of the things, goes back to the manufacturing process again, is the manufacturer going to rotate the material and we just route normally, or are we going to route it any angle type traces on the board to stay away from the fiber weave problems? So those are the kind of things that we need to know right from the beginning. So
two more things with that. The fiber weave, that's where you need to get input from the fabricator to find out what are the options, what do they have available, and how can we help. The other thing that I just remembered is cost. So we talked about loss.
Oh, yeah.
Usually the low loss materials cost more. So are you going to allow some loss and have a marginally functional performance so that you can cut the cost? Or are you going to pay the price and get high performance with a low loss? So again, that depends on what's your target, what's your market for your whatever you're designing.
Engineers always going to pick the most expensive material.
Of course.
and we have to pull them back from the edge and say, you can't build 1 million boards with material that costs 4 times as much. So we have to find that happy medium.
Yeah, it's a trade-off. I mean, you have to look at, what material is going to be the best performance, but what material is going to be the least damage to your pocketbook or to your budget, as well as is the material in stock or is it something that's got to be ordered, and what is the timeline? and how does it fit your schedule to get your widget, to market. And there's a lot of factors that come in when you're thinking about choosing material. Of course, performance is the first one, but you have to look at not just signal integrity, but you also have to look at thermal. Is a material, ability to, what's its ability to handle heat? How does it dissipate heat? And so there's so many different choices in this. I think it's vital to work with your supplier. And I can't stress it enough. Communication
Yeah.
is paramount.
I don't know how many times
So
I've designed boards where engineer wants that perfect board and we get that perfect board and then they change it for, mass production. And then you have a board that just literally fails performance from day one because it's no longer perfect. So,
yeah. So I'll tell you, we're running out of time here, but I know we can go into like routing signals and component placement and via usage. There's so many things to dive into. We could spend all day or all week talking about this, but we'll need to wrap it up. So we're running out of time. But thank you again, both Vernon and Weston, for joining in today's discussion regarding what a PCB layout designer should know about signal integrity. Make sure you join us for future discussions and presentations.
yep.
Hopefully,
Great
we can do
talking to
some
you,
more
Seth.
in-depth
I-
signal integrity in the future.
Yeah.
Oh, definitely. Most definitely.
Yeah, there's there's so much that can be done in a printed circuit board. We could talk for days and days, and hopefully, some people out there want to hear about it and want to listen to us, and we'll bring up some
Mhm.
other subjects down in the comments, and we'll start bringing that information to you.
Most
And we can
definitely. Yep.
tell some more war stories.
Yeah.
Exactly.
All right.
Okay.
Thanks.
Have a good day, Stefan.